When we talk about existential threats to civilization, people usually think about asteroids. They think about killer robots. They think about climate change. They think about nuclear weapons. But there's something that happens on our sun, just a few 100,000 miles away, that could realistically end modern civilization as we know it. Not tomorrow, not in a century, but potentially next year or even this week. And here's the thing that should absolutely terrify you. We're completely unprepared for it. And I mean completely. This isn't a fringe concern. This isn't the worry of a few doomsday preppers in the mountains. This is a scientifically rigorous assessment of our vulnerability. And it's based on physics, history, and engineering. It's based on what we know will happen if the sun does what it's done before. I'm Neil deGrasse Tyson, and what you're about to witness isn't science fiction. It's not speculation. It's not the kind of Hollywood disaster scenario that you watch on the big screen and then dismiss as entertaining but unrealistic. It's a rigorously conducted simulation of what would happen if Earth experienced a direct hit from a solar storm of historic proportions. This isn't hypothetical in the way that "what if we found aliens" is hypothetical. This is something that has happened before, multiple times, in documented history, and based on every measure we have, every instrument, every satellite, every meter of data collected by NASA and ESA and NOAA, it's not a question of if it happens again. It's when. The simulation was conducted over several years by some of the world's leading space physicists, electrical engineers, emergency management experts, and government officials. It was called the 2026 Solar Storm Simulation, though the date in the name doesn't mean it predicted when it would happen. It was just the name of the simulation exercise. The results were sobering enough that multiple governments quietly began increasing their preparedness budgets. Major power utilities began hardening critical infrastructure, and emergency management agencies started dusting off contingency plans that hadn't been seriously updated in decades. But before we dive into the simulation itself, we need to understand what we're actually talking about. What is a solar storm? How does it happen? And why, given that it's such an obvious threat, are we not prepared for it? Let me start with the sun. The sun is a star. That's a fact you learned in school. But understanding what that actually means, what the sun actually is, requires holding in your mind some truly astonishing numbers. The sun is not just a big ball of fire. The sun is a massive nuclear reactor. It's a fusion furnace of incomprehensible power. Every single second, the sun converts roughly 600 million tons of hydrogen into helium. 600 million tons per second. That conversion process releases energy according to Einstein's equation, E equals mc squared. And when you plug in those numbers, when you calculate how much energy is released by converting 600 million tons of mass into energy, you get a number that's almost impossible to comprehend. The sun releases, every second, the energy equivalent of about 3 million atomic bombs. That's not metaphorical. That's the actual physics. That's the actual energy output of the sun, second by second, measured precisely by satellites and confirmed by decades of observations. And here's the truly wild part. The sun is doing this because in its core, at temperatures of about 27 million degrees Fahrenheit, the pressure and temperature are so extreme that hydrogen nuclei, protons, are forced close enough together to fuse into helium nuclei. And when they do that fusion reaction, they release energy. A tiny amount of mass is converted into energy. And that energy is so enormous that it radiates outward from the sun, travels through the vacuum of space, and 93 million miles later, it arrives at Earth, where it drives our weather, powers photosynthesis, and makes all life on Earth possible. So the sun is the ultimate power source for human civilization. Without the sun, there is no life. There is no energy. There is no food. We are, in the most literal sense, powered by nuclear fusion happening 93 million miles away. But the sun is not a stable, uniform ball of radiation. It's not a calm, peaceful source of energy. The sun is turbulent. It's chaotic. It has weather just like Earth does. And occasionally, the sun has really bad weather. Now, the sun's surface, what we call the photosphere, is about 10,000 degrees Fahrenheit. That's hot. That's the kind of temperature that would vaporize any material we have. But here's something that puzzled astrophysicists for decades. The corona, the sun's outer atmosphere, is significantly hotter than the surface. We're talking about 1,000,000 degrees or more. How is that possible? How is the thing farther away from the heat source hotter than the thing closer to it? It shouldn't be possible according to basic thermodynamic intuition. But the sun doesn't care about our intuition. What's actually happening is that the sun's magnetic field, which is created by the movement of charged plasma in the sun's interior, extends upward into the corona. And that magnetic field gets twisted and tangled and compressed as the sun rotates and as plasma churns beneath the surface. The magnetic field lines, those invisible threads of magnetic force, get bent and twisted until they're under enormous tension. And occasionally, when the tension becomes too great, when the magnetic field can't hold the stress anymore, something gives way. The field lines snap. They reconnect. And when they do, they release energy in one of the most violent ways imaginable. That's called a solar flare. A solar flare is a sudden, enormous release of radiation across the entire electromagnetic spectrum. Radio waves, microwave radiation, infrared, visible light, ultraviolet, X-rays, gamma rays, all of it released in a burst that lasts anywhere from minutes to hours. The energy released in a single large solar flare is equivalent to millions of atomic bombs going off simultaneously. Think about that for a second. A single solar flare, an event that happens frequently on the sun, releases more energy than all of human civilization uses in a year. It's like the sun occasionally decides to have a temper tantrum, and when it does, it throws around energy in a way that makes our most powerful weapons look like firecrackers. But here's the thing. Solar flares, while enormously powerful, aren't necessarily the most destructive thing that the sun can throw at us. A solar flare is radiation, travels at the speed of light. It arrives at Earth in about 8 minutes. It can disrupt radio communications, it can damage satellites, it can affect electronics. But it's not a physical thing. It's not a wave of matter. What can be even more destructive is the coronal mass ejection. And this is where things get really dangerous. A coronal mass ejection, or CME, is what happens when the tension in the sun's magnetic field becomes so great that not just radiation is released, but actual mass, actual matter from the sun's atmosphere, is ejected into space. We're talking about billions of tons of superheated, magnetized plasma being thrown out into space at speeds that can exceed 7,000 kilometers per hour. Imagine 1 billion tons of matter, superheated to millions of degrees, somehow suspended in a magnetic field, and all of it moving toward you at speeds of thousands of kilometers per hour. Now imagine that this happens on a regular basis on the sun. These coronal mass ejections travel through space. They expand as they travel. They carry the sun's magnetic field with them. And if Earth happens to be in the path of one of these ejections, if our planet is in the right place at the right time to get hit by this bubble of superheated plasma, then we're going to have a problem. Now, you might think that when this bubble of plasma reaches Earth, it would hit our atmosphere, and our atmosphere would protect us. Our atmosphere is pretty good at protecting us from most things. It blocks ultraviolet radiation from the sun, keeps most meteors from reaching the ground. It insulates us from the vacuum of space. But a coronal mass ejection isn't like that. It's not particles slamming into air molecules where the air provides a protective barrier. It's a magnetized bubble of plasma, essentially the sun's own atmosphere, colliding with Earth's magnetic field. Earth's magnetic field is also known as the magnetosphere. It's generated by the movement of liquid iron in Earth's outer core, which acts like a giant dynamo, creating a planetary-scale magnetic field. This field extends far into space, creating a shield around Earth. Without this field, we'd be bombarded directly by the solar wind, and life as we know it would not exist. So when a coronal mass ejection encounters Earth's magnetosphere, it's essentially one magnetic field colliding with another magnetic field. The two magnetic fields don't merge smoothly. Instead, there's a region of intense interaction. The magnetic field lines from the CME and the magnetic field lines from Earth's magnetosphere get tangled up together. And in this region of chaos and extreme magnetic field gradients, something called magnetic reconnection occurs. Magnetic reconnection is when the magnetic field lines of two opposite polarity reconnect, rearranging themselves in a lower energy configuration. But all that energy that was stored in the configuration of the field lines doesn't disappear. It gets released. and it gets released as kinetic energy, as movement. Particles get accelerated to enormous speeds. Protons and electrons spiral along Earth's magnetic field lines at near light-speed velocities. These high-energy particles rain down on Earth's upper atmosphere, particularly in the polar regions where the magnetic field lines converge. When these particles collide with atoms and molecules in our atmosphere, primarily oxygen and nitrogen, they excite those atoms and molecules to higher energy levels. And when those atoms and molecules drop back down to their ground state, they release energy as light. That light is what we see as an aurora, the beautiful, dancing lights in the night sky, the northern lights or aurora borealis, the southern lights or aurora australis. That beautiful light show is actually the visual signature of particles from the sun slamming into our atmosphere at tremendous speeds, transferring energy to the atoms there, and then those atoms releasing that energy as visible light. In a mild geomagnetic storm, the auroras are beautiful and visible to people at high latitudes. In a severe geomagnetic storm, the auroras can be visible much farther south, even at temperate latitudes where they're almost never seen. In the most severe storms in recorded history, the auroras were visible at the equator. But here's the key point. The auroras, beautiful as they are a visible symptom of something far more dangerous happening to our infrastructure. Because when the geomagnetically induced currents start flowing through Earth's atmosphere and Earth's magnetic field, those same currents also flow through our planet's surface. And anything that's a good conductor of electricity, anything like copper wires or metal structures, becomes a path for those currents. And the most extensive electrical conductor network we have is our power grid. The electrical grid is a marvel of engineering. It's a system of power plants, transformers, transmission lines, and distribution systems designed to generate electricity at centralized locations and deliver it to millions of homes and businesses. It's one of the most important pieces of infrastructure we have. Virtually every aspect of modern civilization depends on it. A typical power grid works like this. At a power plant, electricity is generated either by burning coal, using nuclear fission, from wind turbines, from solar panels, or from other sources. That electricity is then stepped up in voltage by large transformers. High voltage is more efficient for transmitting power over long distances because it reduces losses. The electricity travels along transmission lines, which are the big towers you see carrying power across the landscape. Those transmission lines can carry electricity from the power plant hundreds of miles away. When the electricity gets close to where it's needed, it goes through substations where large transformers step the voltage back down to a level that's safe for distribution to homes and businesses. This whole system is incredible. It's allowed us to generate electricity in places where it's easiest to generate it and deliver it to places where it's needed. It's scalable. It's reliable. It works extraordinarily well under normal conditions. But it has a weakness, and that weakness is the large power transformers that step voltage up and down. A large power transformer is a massive piece of equipment. Some of them weigh hundreds of tons. They're custom engineered for specific locations. They're full of transformer oil that both insulates and cools the windings. The electrical coils inside are wrapped with insulating material that keeps the current from arcing between turns. These transformers are built to handle the electrical load and voltage that flows through them under normal circumstances. They're built with safety margins. But they're not built to handle arbitrary electrical currents flowing through them in arbitrary directions. Now, when a geomagnetic storm occurs, when the Earth's magnetic field is fluctuating wildly, something interesting happens. Those fluctuating magnetic fields induce electrical currents in any long conductor on or near Earth's surface. It's a phenomenon called electromagnetic induction. A changing magnetic field induces an electric field, which drives current through conductors. The power grid is a perfect target for this effect. The long transmission lines are excellent conductors. When a geomagnetic storm creates a fluctuating magnetic field, currents get induced in those transmission lines. These are called geomagnetically induced currents, or GICs. Now, here's the critical part. GICs often flow in directions and magnitudes that the power system was never designed to handle. They flow through transformers in the wrong direction. They create harmonic distortion in the electrical system. They cause overvoltage conditions. and the equipment that was engineered to handle normal power flow starts experiencing stress that it wasn't designed for. In a mild geomagnetic storm, the GICs might be small enough that the system can handle them without major problems. The transformers might get a little hot. The system might be stressed, but it survives. But in a severe geomagnetic storm, the GICs can be enormous. The currents flowing through large transformers can exceed their design capacity. The insulating materials inside the transformer start to break down. The transformer oil heats up, and if the current is large enough and persists long enough, the transformer can suffer permanent damage. This is exactly what happened during the Quebec blackout of March 13, 1989. On that date, a moderate geomagnetic storm, the kind that occurs when solar activity is high, induced currents in the power system serving Quebec. One particular large transformer at a substation called La Grande was hit with a geomagnetically induced current. The current damaged the transformer's insulation. The transformer failed, and when that large transformer failed, the power it was carrying had to be rerouted through the rest of the grid. That rerouting caused other transformers to carry more current than they were designed for. Those transformers became stressed. Their protective relays, safety switches designed to disconnect them from the grid if they detect a problem, started tripping. More transformers went offline. The cascade accelerated. Within 9 hours, the entire grid serving Quebec suffered a blackout. 6 million people lost power. In the middle of winter, in Canada, it was a significant crisis. People died of cold. Hospitals had to shift to backup power. The economic damage was significant. But here's the crucial part. The 1989 Quebec blackout was caused by a moderate geomagnetic storm, not a severe one, not the kind of storm we're really worried about. The storm we're really worried about is something like the one that happened in 1859. In May of 1859, astronomers observed something remarkable happening on the sun. They observed bright flares, sudden bursts of light, appearing on the solar surface. This was unusual enough to note, but what happened next was unprecedented. The sun unleashed a coronal mass ejection of staggering proportions. The ejection was so powerful that the shock wave associated with it arrived at Earth in roughly 18 hours, an extraordinarily fast transit. The pressure of this ejection compressed Earth's magnetosphere dramatically. The geomagnetic storm that resulted was the most powerful ever recorded by human civilization. It was so intense that it created auroras visible across the entire planet. In the tropics and at temperate latitudes where auroras are virtually never seen, the sky lit up with dancing green and red lights. In some places, the light was bright enough to read a newspaper by at midnight. The auroras were visible even during twilight hours. In Australia and Hawaii, the sky reportedly turned as red as blood. But the most important effect of this geomagnetic storm was what happened to the telegraph system, which was the cutting-edge communication technology of the time. Telegraph operators worldwide reported something extraordinary. The geomagnetically induced currents flowing through the telegraph lines were so strong that they were affecting the equipment. Operators reported receiving electrical shocks so severe that they were knocked out of their chairs. One operator in Boston was severely shocked. Another operator in England reported that the induced currents in the telegraph lines were so strong that he could disconnect the battery, the power source, and the system would still function, powered entirely by the geomagnetically induced current. Telegraph equipment caught fire. Telegraph networks across the continent simply ceased to function. The interconnected communication system of the era, the thing that connected people across vast distances, was knocked offline. Now, here's the critical insight. In 1859, the telegraph was the height of technology. It was how people communicated across distances. But it was not the only way to function. People could still send messages by postal mail. Commerce could still happen by ship. Cities could still function without telegraphy. But imagine if that same event happened today. Imagine if the sun threw a coronal mass ejection directly at Earth, one with the same magnitude as the event of 1859. But this time, instead of hitting a civilization that's dependent on telegraphy, it hits a civilization dependent on electricity, computers, the internet, and digital systems for everything. This is what the 2026 solar storm simulation set out to model. The simulation was conducted by space physicists from NOAA, the National Oceanic and Atmospheric Administration, as well as researchers from universities, from the Department of Energy, from NASA, and from various electrical utilities and emergency management agencies. It took several years to conduct properly. They had to model the solar physics accurately. They had to understand what a 1859 class solar storm would actually do to Earth's magnetosphere. They had to model the induced currents in the power grid. They had to model how the protective systems in the grid would respond. They had to model the cascade of failures that would follow. The result was a minute-by-minute, hour-by-hour timeline of what would actually happen if Earth got directly hit by a coronal mass ejection equivalent in power to the Carrington Event of 1859. And what they found was absolutely terrifying. Let's walk through the simulation. The simulation begins with the assumption that the Sun produces a coronal mass ejection of equivalent size and direction to the Carrington Event. Physicists calculated the speed of this ejection based on observations of similar events in modern times. They estimated a speed of approximately 7,200 kilometers per hour, incredibly fast, but not unreasonable based on historical data and observations of modern CMEs. At this speed, a coronal mass ejection takes about 18 to 22 hours to travel from the Sun to Earth. But we would get warning before it arrived. NASA operates a satellite called the Advanced Composition Explorer, or ACE, located at a point in space called L1, the first Lagrange point. This is a location about 1 million miles from Earth, positioned between Earth and the Sun, where the gravitational forces from the Sun and Earth balance out. ACE sits at this location and constantly monitors the solar wind, the stream of charged particles and magnetic fields constantly flowing outward from the Sun. If a coronal mass ejection is heading toward Earth, ACE is positioned perfectly to see it first. When a CME arrives at ACE's location, ACE detects the sudden change in the solar wind speed and density. The ACE spacecraft and other sensors at L1 can detect a coronal mass ejection roughly 15 to 45 minutes before it reaches Earth, depending on the speed of the ejection. In the simulation, this warning came through at 10:47 a.m. Eastern Time on a Tuesday in November. This was a realistic choice of timing. The simulation wanted to see what would happen in autumn, with winter approaching. ACE detected the sudden increase in solar wind speed and density characteristic of a fast coronal mass ejection. The data was telemetered back to Earth. At NOAA's Space Weather Prediction Center in Boulder, Colorado, operators saw the alert. They immediately issued a warning. A geomagnetic storm watch was issued. The highest level alert available from NOAA was posted to their website. But here's the thing about 15 to 45 minutes of warning. It's enough time to know that something is coming, but it's not nearly enough time to do anything about it on a large scale. You can't shut down a power grid in 15 minutes. It's not like flipping a switch. The power grid is a constantly changing system. There's always demand for electricity. There are always generators running to meet that demand. If you suddenly try to shut down large generators or disconnect major transmission lines, you risk causing a blackout even before the solar storm hits. The best you can do in 15 minutes of warning is to issue warnings to the public that power might go out, prepare backup systems, alert emergency services. But you can't prevent what's coming. At 11:04 a.m. Eastern Time, the coronal mass ejection made contact with Earth's magnetosphere. What happened next unfolded over the course of several hours, but the consequences would be felt for years. The initial collision was violent. The density of the solar wind jumped from its normal 5 to 10 particles per cubic centimeter to over 50 particles per cubic centimeter in a matter of seconds. The magnetic field of Earth's magnetosphere compressed dramatically. The bow shock, the region where the solar wind meets the magnetosphere, was pushed inward, right toward Earth's surface. The pressure from the CME squeezed Earth's magnetic field. And as the field lines reorganized, as magnetic reconnection occurred, they released enormous amounts of energy. This energy accelerated particles to tremendous speeds. Protons and electrons spiraled into the upper atmosphere, creating intense auroras at high latitudes. But simultaneously, the changing magnetic field was inducing enormous currents in the power system. Within minutes of the CME's contact with the magnetosphere, geomagnetically induced currents began flowing through the power grid. These weren't small currents. In a storm of this magnitude, The currents were orders of magnitude larger than anything the grid had been designed to handle. The induced currents were particularly strong in the large transformers, the massive devices that step voltage up and down throughout the system. In substations across North America, transformers that had been designed to handle tens of thousands of amps were suddenly experiencing currents in directions they weren't engineered for. One critical thing to understand about power transformers: they have protective relays. These are electrical switches designed to automatically disconnect a transformer from the power grid if something goes wrong. If the voltage gets too high, if the current gets too high, if there's a fault condition, the relay will trip and disconnect the transformer. These relays are designed to protect the transformer from damage. But in a situation where currents are being induced throughout the entire grid simultaneously, the relays face an unprecedented situation. There's no local fault, the problem is systemic, affecting many transformers across a huge area. In addition, the protective systems of the power grid were designed with the assumption that failures would be local and isolated. If a transformer fails in one location, the rest of the grid remains intact. The power the failed transformer was carrying gets rerouted through the rest of the system. But in the simulation, many transformers were being hit with geomagnetically induced currents simultaneously. Multiple transformers across the continent were being damaged or destroyed at the same time. At 11:23 a.m., the first major transformer failure was recorded in the simulation. A large transformer at a substation in northern Illinois experienced a surge of geomagnetically induced current that exceeded its capacity. The insulation around the core, the material that keeps the electrical winding separate from the core and from other windings, began to break down. Within seconds, the transformer was sparking internally. Within minutes, it was destroyed. But the power that transformer had been transmitting didn't just disappear. It had to go somewhere. The power flow through the transmission system was rerouted through other paths. The demand that had been distributed through that transformer was now concentrated on other transformers and transmission lines. This caused those other transformers to carry more current than they were designed for. They became stressed. Their protective relays started detecting abnormal conditions. The voltage in their areas of the system started to rise. The frequency of the alternating current started to fluctuate. By 11:34 a.m., another major transformer failed, and another. By 11:47 a.m., multiple failures were occurring. The cascade had begun. When power grid components fail in rapid succession, the protective systems that are supposed to isolate local problems start to create a broader blackout. A protective relay trips to isolate a failed transformer. But that isolation causes the power from that part of the grid to be rerouted elsewhere, overloading that elsewhere. More relays trip. The blackout spreads. In the simulation, the process accelerated. More and more transformers were experiencing currents that exceeded their capacity. More and more protective relays were tripping. The failures were happening too fast across too wide an area for the automated systems to respond intelligently. By 12:03 p.m. Eastern Time, less than an hour after the CME made contact with the magnetosphere, the Eastern Interconnection suffered a catastrophic cascading blackout. The Eastern Interconnection is the massive electrical grid that covers roughly the eastern half of North America. It extends from the Great Plains in the west to the Atlantic coast in the east. It covers Canada, the United States, and parts of Mexico. It serves a population of more than 100 million people. And it went dark. This didn't happen everywhere at exactly the same moment. The blackout spread across the region as protective systems sequentially isolated damaged sections. But what it meant was that tens of millions of people lost electrical power simultaneously. New York City went dark at 12:17 p.m. The Statue of Liberty went dark. The Empire State Building went dark. Times Square, one of the brightest places on Earth, went dark. Subway systems halted. Traffic lights went out. Hospitals switched to backup power. Boston went dark at 12:19 p.m. Philadelphia at 12:11 p.m. Washington, D.C. at 12:21 p.m. The entire Mid-Atlantic corridor, one of the most densely populated regions on Earth, lost power within minutes. And the power didn't come back on. It didn't come back on in 5 minutes. It didn't come back on in 5 hours. In the simulation, it didn't come back on for days. Now, here's something crucial to understand about how the electrical grid actually works. Power plants can't just be turned off and back on like a light switch. The process of restarting a power plant is complex and time-consuming. When a power plant loses external electrical power, when the grid goes down, the plant needs to restart using internal backup power. Most large power plants have what are called black start units, backup diesel generators, that can provide enough power to restart the plant's internal systems. But the process takes time. It can take hours to get a large power plant fully restarted and synchronized with the grid. But here's the bigger problem. In a situation where the entire grid has gone down, thousands of power plants across the continent are in the dark simultaneously. They all need to be restarted. They all need to be carefully synchronized with each other. If two power plants try to connect to the grid at slightly different frequencies or phases, the resulting surge can damage both plants. This is called the restart problem. In a cascading blackout of this magnitude, the grid can't just be turned back on. It has to be carefully rebuilt, region by region, linking power plants back together in a coordinated sequence. The process is incredibly complex. In the simulation, military coordination between NERC, the North American Electric Reliability Corporation, and various grid operators attempted to perform a systematic restart. They started with the least damaged parts of the grid. They brought power plants back online one by one. They checked frequency and phase. They slowly connected regions back together. In the best-case scenario of the simulation, it took 7 days to partially restore the eastern grid. 7 days. But that was the best case, where power plants weren't severely damaged and where the transformers hadn't been destroyed. But the transformers had been destroyed. The simulation estimated that approximately 2,000 large high-voltage power transformers across North America would suffer damage severe enough to require replacement. Now, think about that number. That's a significant fraction of the entire continent's large power transformer fleet. And these aren't replaceable in days or weeks. A large power transformer is custom engineered. It takes about 4 to 6 months to manufacture one. The global manufacturing capacity for large transformers is roughly 400 to 500 units per year across all manufacturers. That means that if you suddenly needed 2,000 replacement transformers, you couldn't manufacture them fast enough to restore the grid in the expected time frame. The simulation calculated that it would take 4 to 5 years to manufacture and install enough replacement transformers to fully restore the North American grid to its previous capacity. 4 to 5 years. Think about that. 4 to 5 years without electrical power to much of North America. That's not a temporary inconvenience. That's a fundamental change to civilization. As the day of the blackout progressed, the full scope of the disaster began to become apparent. At 4:30 p.m., the first water treatment plants began losing pressure. Without electrical power to run the pumps that pressurized the system, water was no longer flowing to taps. Water is essential. Water is required for drinking, for sanitation, for fighting fires. Without water, cities can't function. Water pressure dropped throughout the affected region. In New York City, water pressure dropped to dangerous levels by evening. In many areas, water pressure was completely lost by midnight. Hospitals had to resort to using bottled water for sanitation. Residents had no water for basic sanitation, drinking, or cooking. At 6:15 p.m., hospitals across the affected region switched to backup power. Every hospital has backup generators, usually diesel-powered, that are designed to keep critical systems running during brief power outages. But these generators are only designed to run for a few hours. They have fuel tanks that can power the generator for maybe 24 to 48 hours of continuous operation. Hospital administrators began calculating how long their fuel would last. They started thinking about how they would triage patients if backup power ran out. They thought about which systems were most critical life support for patients in intensive care, operating rooms, emergency departments. They began to accept the reality that they would have to make impossible choices. At 7:45 p.m., mobile phone networks started going offline. Cell towers require constant electrical power. When the grid went down, they switched to backup batteries. But after a few hours, those batteries were depleted. Without power to recharge them, the cell networks went dark. By 10 p.m., There was essentially no cell phone service across the entire eastern seaboard. Millions of people who depended on cell phones for communication suddenly found those phones useless. The loss of cell networks meant the loss of the primary communication method for the entire affected population. This had cascading effects. Emergency services couldn't use their usual communication systems. Families couldn't reach each other. Businesses couldn't communicate with employees. The National Guard couldn't easily communicate with the public. At 9:30 p.m., grocery stores were still open, but they were operating on emergency lighting, generators, or battery-powered lights. The store's refrigeration systems had been off for nearly 10 hours. Frozen food was starting to thaw. Refrigerated food was warming up. Store managers made a decision. They opened their doors and told people to take whatever they wanted. Give the food away rather than watch it rot. But within an hour, the situation escalated. As evening deepened and people began to realize that power wasn't coming back on in a few hours, panic buying started in earnest. Crowds of people descended on grocery stores. People filled shopping carts with whatever they could find. People were thinking about their families, about feeding their children, about the upcoming days without electricity. They were thinking about winter approaching and wondering how they would stay warm. The panic was very rational. It was the logical response to the realization that critical supplies, food, were about to become scarce. By midnight on the day of the storm, most major grocery stores in the affected region were stripped bare. Food was gone. Shelves were empty. At 11:15 p.m., the first traffic accidents began piling up. Without electricity, traffic lights went dark. At major intersections across the eastern seaboard, traffic lights simply stopped working. Intersections that were normally managed by synchronized lights became chaotic. Police tried to direct traffic manually at critical intersections, but they were overwhelmed. There were too many intersections, too many accidents. Emergency services were receiving hundreds of reports of accidents, but with no electricity, no phones, and no cell networks to coordinate response, the ability to respond was severely hampered. Ambulances had to navigate dark city streets. Emergency responders couldn't communicate with each other. The emergency response system was itself becoming overwhelmed by the chaos of the blackout. At 2 a.m. on the second day after the storm, the true scope of the situation in New York City was becoming apparent. Nearly 8 million people without power, no water, no phones, no traffic lights, no way to cook food, no way to see at night beyond what flashlights and candles could provide. The streets were dark. The city, which normally glows with hundreds of millions of lights, was essentially blacked out. The darkness was almost unimaginable for a city that had not experienced true darkness in over a century. But the worst was yet to come. You see, what the simulation revealed was that the initial power outage, catastrophic as it was only the beginning. The real disaster was what happened next, in the hours and days and weeks following the blackout. Here's something we don't often think about. Modern civilization is entirely dependent on electrical power and the digital systems it enables. And I want to emphasize that word, entirely. This is not an exaggeration to make for dramatic effect. It's not hyperbole. It's the literal truth. Our food supply depends on electrical power. Our water system depends on electrical power. Our medical system depends on electrical power. Our financial system depends on electrical power. Our communication system depends on electrical power. Everything depends on it. Remove electrical power from a modern city, and you don't get something that looks like a minor inconvenience. You don't get something that looks like the blackouts of the 1970s, where people adapted and got through it. You get a cascade of failures that undermine the basic functioning of civilization. By the morning of November 5th, the second day of the blackout, the food situation in New York City was already critical. Grocery stores were empty. Restaurants were closed because they had no power and no water. Food deliveries had stopped because truck drivers couldn't get fuel at gas stations. Gas stations, with no electricity, couldn't pump fuel from their underground tanks. Food that was in homes started to spoil. Without refrigeration, meat went bad. Vegetables started to rot. Ice in freezers melted. Anything that required refrigeration was at risk. people realized something profound. They had maybe enough food in their homes for a few days. Maybe a week if they were very lucky and had well-stocked pantries. But beyond that, there would be no food available in stores. There would be no food deliveries. There would be no restaurants. This was a crisis situation unfolding in real time. By noon on the second day, the first looting began in earnest. I want to be clear about something. This wasn't random chaos. This was rational behavior. People understood the situation. They understood that formal order, the system of law enforcement and commerce, was breaking down. They understood that food was becoming scarce, and scarcity creates competition. In the absence of electricity, in the absence of functioning phone systems, police couldn't coordinate. They couldn't respond to every call for help. And as the number of people in crisis grew, as more and more people realized they didn't have enough food and were desperate, the ability of law enforcement to maintain order diminished rapidly. Some people broke into stores to take food. Some broke into homes to find supplies. Others tried to hoard fuel or gasoline or medicine. It wasn't organized criminal activity. It was desperate individuals and families trying to survive. Water was the acute crisis. In a modern city with millions of people, water doesn't arrive at homes through gravity alone. It has to be pumped. The water treatment plants have to operate. The distribution system has to maintain pressure. All of this requires electrical power and the operation of complex mechanical systems. Without electrical power, gravity and water pressure alone can sustain supply to upper floors for a limited time, but for lower floors and for the city as a whole, you need pumps running 24 hours a day. By the afternoon of the second day, water pressure in most of New York City was essentially gone. People couldn't flush toilets. They couldn't shower. They couldn't clean. If a fire broke out, there was no water to fight it with. Consider what that means. You can't maintain sanitation without water. You can't prevent disease. You can't live in a way that's even minimally hygienic. Inevitably, fires started. Without working electrical systems for fire detection and suppression, without water pressure to fight fires, fires spread. Some were caused by accidents, people trying to cook with candles, candles falling over, things igniting. Some were caused by accidents in the dark, people falling and injuring themselves near open flames. By the evening of the second day, the simulation estimated that roughly 50 million people in the eastern United States were without power, without water, without phones, and without access to food beyond what they had in their homes. 50 million people. That's the entire population of Spain. That's the entire population of California and Texas combined. 50 million people in a state of crisis. At 10 p.m. on the second day, the first disease outbreaks were confirmed. This wasn't surprising, it was predicted. Without water for sanitation, without the ability to flush toilets, without the ability to clean, disease spreads. Dysentery and other waterborne illnesses started spreading within hours of water pressure being lost. In dense urban areas, where millions of people live in close proximity to each other, disease spreads incredibly fast. In addition, without refrigeration, food spoiled rapidly. Contamination was inevitable. People ate spoiled food because they were desperate and hungry. They drank contaminated water because they had no choice. Disease spread. By the end of the second day, the simulation showed documented cases of gastrointestinal illness across the affected region. By the end of the third day, the number of cases had multiplied. By 48 hours into the blackout, the National Guard was being mobilized. The Department of Defense was activating contingency plans that had never been implemented at this scale. The President of the United States declared a national emergency and invoked the Defense Production Act. But here's the thing. In a situation where there's no electricity, no phones, and no internet, how do you mobilize resources? How do you coordinate? How do you prevent total societal breakdown? The military used radio systems, which don't depend on the civilian infrastructure, to attempt coordination. But the scale of the disaster was overwhelming. You're trying to respond to a crisis affecting 50 million people with an emergency response infrastructure designed to handle disasters affecting thousands or maybe millions, not tens of millions. The simulation ran through a series of scenarios of how the first 2 weeks of the blackout would unfold. In nearly all of them, the conclusion was the same. The first 2 weeks would be the most critical. In those first 2 weeks, you would either prevent complete societal collapse or you wouldn't. The key resources were fuel, food, and water. Fuel was the most immediately critical. Gasoline for vehicles was essential. Without fuel, vehicles couldn't run. Without vehicles, food couldn't be delivered. Without delivered food, people would starve. And starving people, desperate people, take things by force. Gas stations had fuel in their underground tanks, but without electricity, the pumps couldn't work. Some gas stations had backup generators and could continue to pump fuel for a while. But there were only so many gas stations, only so much fuel. The military tried to establish supply lines using military fuel reserves. But the military controls only a fraction of the fuel that civilian society needs. Military fuel reserves are designed to meet military needs, not to sustain civilian society. Within days, fuel became desperately scarce. Vehicles that had gas tanks full started to run out. Drivers competed for the remaining fuel at stations that still had electricity to pump it. Food was the next critical resource. The grocery stores that were stripped bare on day one of the blackout meant that the only food available after that was what people had in their homes or what they could find by scavenging or by obtaining through the black market or through force. But people's homes typically have enough food for a week or 2 at most. Some homes have more if people regularly stock food. But the average home doesn't have a month's worth of food just sitting in the pantry. The simulation estimated that by day 5, the situation in major cities would be approaching genuine famine conditions. People would be desperate. They would be hungry. They would be willing to take things by force to feed their families. The police and National Guard couldn't feed 50 million people. Even with the most generous interpretation of what they could accomplish, even if they somehow had adequate supplies, they couldn't distribute those supplies to 50 million people fast enough. The logistics were impossible. But let's zoom out for a moment and look at what was happening at the national level and then at the global level. The power grid failure in the eastern United States affected not just homes and businesses. It affected critical infrastructure nationwide and globally. The Federal Reserve, which is physically located in New York, was running on backup power. But the Federal Reserve's electronic systems, the servers, the computers, the networks that track the money supply, that maintain records of who owns what, that facilitate banking, were essentially offline. The Federal Reserve couldn't access its own systems to determine what reserves it had. Banks couldn't access Federal Reserve systems to verify that the money in their accounts was actually there. Transactions couldn't be processed. The banking system is built on the assumption that electronic systems work. When those systems fail, the entire system seizes up. In cities across the country, ATMs, automated teller machines, went offline. People couldn't access their money. Cash suddenly became a precious commodity. People who relied on electronic banking suddenly couldn't access their accounts. The financial system ran on information. When the information infrastructure failed, the financial system lost the ability to function. The simulation showed that by day 3 of the blackout, stock markets had closed. By day 4, international markets were starting to suspect that the U.S. financial system was in collapse. Countries worldwide were asking, is the U.S. financial system still functioning? Are U.S. banks solvent? Are U.S. dollar deposits safe? By day 6, there was genuine risk that global financial panic would set in. Investors worldwide would start dumping dollar-denominated assets. International trade would halt because buyers and sellers couldn't pay for goods. The global economy would essentially stop. Here's the thing about a global financial system. It's based on confidence and digital communication. When both of those fail, the whole thing can unravel very rapidly. We've seen this on smaller scales during financial crises. The 2008 financial crisis came within days of a total system collapse. What saved the system was the Federal Reserve stepping in and essentially guaranteeing that the system wouldn't fail. But in a scenario where there's no electricity, no communication systems, and no functioning government ability to transfer money or guarantee anything, even that kind of intervention becomes impossible. The simulation showed that by 1 week into the blackout, the global financial system would be in genuine crisis. Banks worldwide would be unable to verify that their deposits were still there. The credit system would freeze. Capital would be frozen. Trade would stop. The economic damage wouldn't just be limited to the power outage, it would cascade through the global system. Economists calculated the costs. The immediate damage from the power outage itself, destroyed transformers, damaged generators, lost production, was estimated at several $100 billion. But the cascading economic damage from the breakdown of financial systems, the halting of global trade, the disruption of supply chains worldwide, that was estimated at somewhere in the range of $5 to $10 trillion, with the most pessimistic estimates going even higher. That's roughly the size of the entire US economy in annual GDP. That's a civilization-wide catastrophic economic impact. But the human cost was what really kept the simulation modelers awake at night. By day 10 of the blackout, the mortality rate in major cities was climbing rapidly. In addition to the expected deaths from food shortages and disease, there were also deaths from the breakdown of medical services. Hospitals, running out of fuel for backup generators, began shutting down. Not all at once, but progressively. As fuel ran low, hospitals had to make decisions about what systems to keep running and what systems to shut down. They couldn't run everything on limited fuel. Operating rooms shut down. Elective surgery stopped. Intensive care units had to reduce the number of patients they could serve. Eventually, as fuel ran critically low, hospitals made the decision to discharge patients when possible and to focus resources on emergency care only. Kidney dialysis clinics, which require electricity for every single patient to run the dialysis machines that filter blood, closed. There were roughly 500,000 people in the United States dependent on dialysis to stay alive. These people need dialysis 3 times a week. Without dialysis, their kidneys can't filter waste products from their blood. Waste accumulates. They get sick. They die. The simulation estimated that within weeks, thousands of dialysis-dependent patients had died simply because the dialysis centers had no power and couldn't operate. An insulin-dependent diabetic without refrigeration for their insulin has maybe a few days before their medication spoils and becomes useless. There are millions of insulin-dependent diabetics in North America. Refrigerated insulin is essential to keep them alive. Millions of people have chronic conditions that depend on medication stored in refrigerators. EpiPens for severe allergies, vaccines, insulin, medications for heart conditions. Without that refrigeration, those medications become useless. The simulation estimated that the deaths directly attributable to the blackout and its immediate consequences, starvation, disease, medical crises, cold in the winter, would total in the hundreds of thousands by the end of the first month. By the end of 3 months, that number could climb into the millions. If we're talking about an 1859-level solar storm hitting during winter, the death toll could potentially exceed millions just in the first year. As people froze without heat and the cascade of failures continued to unfold. Let me put that in perspective. The death toll from this type of event could rival the death toll from World War II. Could rival the 1918 Spanish flu pandemic. This is a civilization-wide catastrophe. But again, let me emphasize, this assumes that the transformers and the grid are the only casualties of the solar storm. The simulation also had to account for other effects. You see, a geomagnetic storm doesn't just induce currents in power lines. It also damages satellites. In fact, severe geomagnetic storms have historically been the primary cause of satellite damage. When the radiation environment in Earth's magnetosphere becomes extremely intense, which happens during a severe geomagnetic storm, satellites are exposed to that radiation. Solar cells degrade. Electronics suffer radiation damage. Satellite systems fail. There are roughly 5,000 to 10,000 satellites in Earth orbit at any given time. During a severe geomagnetic storm, a significant fraction of them would be damaged. GPS satellites, communications satellites, weather satellites, scientific research satellites. In the simulation, roughly 40% of the satellites in low Earth orbit were damaged in the first 24 hours of the storm. Some were completely destroyed. Others were damaged but could potentially be repaired or reprogrammed. But the loss of satellite capability would be severe. The loss of GPS constellation satellites was particularly catastrophic. Modern civilization relies on GPS for far more than just navigation. Yes, we use it for GPS navigation in our cars, but that's almost incidental to what GPS is really used for. The financial system uses GPS for time synchronization. Every financial transaction needs an accurate timestamp. Banks, stock exchanges, foreign exchange markets, they all depend on GPS for precise, synchronized timekeeping. Power plants use GPS for synchronization. The power grid operates at a frequency of 60 Hz in North America. That frequency has to be maintained within strict tolerances. GPS satellites provide the atomic clocks that allow power plants to synchronize their frequency to the grid. Cellular networks use GPS. The towers that make up the cellular network need to be synchronized. Without synchronization, the network falls apart. Emergency services use GPS. Police, fire, ambulance services all use GPS for dispatching and coordination. Removing GPS from the equation doesn't just mean you can't use your phone's navigation app. It means that entire systems that depend on GPS for precise timing lose their ability to function. The simulation estimated that the loss of satellites would extend the recovery time by additional months or even years in some cases. Communications infrastructure was also heavily affected. Beyond the cellular networks, which had gone offline due to lack of power, there's the internet backbone, the undersea cables that carry the vast majority of international communications. These cables don't rely on ground-based power in the same way that cellular networks do. They have their own power systems, but they do rely on shore stations and internet exchanges, many of which are powered by the electrical grid. When the grid went down in the eastern United States, a significant portion of the internet's infrastructure went dark. The simulation showed that approximately 30 to 40% of the internet's capacity would be lost in the first days of the blackout. International communications would be severely degraded. Governments would have difficulty coordinating responses with other nations. The world's ability to understand what was happening would itself be compromised. Now, let's think about what was happening outside the United States. The coronal mass ejection in the simulation primarily affected the Western Hemisphere. The storm was strongest in the Americas, but geomagnetic storms have a global impact. The effects are strongest at high magnetic latitudes, which is why Canada and northern Scandinavia would be hit hardest. But there were significant effects at mid-latitudes worldwide. In Europe, power grids experienced significant damage, but the effects were somewhat less severe than in North America. The European power grid is smaller than the North American grid and more compartmentalized. Still, major blackouts were experienced across large portions of the continent. In particular, Northern Europe, Scandinavia, the Baltic states, northern Germany, Scotland experienced severe blackouts. The aurora caused by the geomagnetic storm would have been visible across the entire continent. In Asia, particularly in countries like Japan, which sits at the boundary of severe geomagnetic effects, power systems experienced significant stress. Japan, being an island nation dependent on imports for a large portion of its energy and food, relies heavily on just-in-time supply chains that depend on functioning transportation and communication systems. The disruption of global trade that followed the blackout had devastating effects on Japanese manufacturing and exports. Australia, being in the southern hemisphere, would have experienced less severe geomagnetic effects. The power grid could potentially have maintained operation or had only partial outages. But Australia exports enormous amounts of food. If global supply chains broke down, Australia's economy would still suffer catastrophic damage due to the loss of export markets. The simulation showed that globally, the outage and its cascading consequences would affect billions of people. Agricultural disruption would be global. Modern agriculture depends on electrical power for irrigation, for refrigeration and transportation of crops, for processing. A global disruption of agriculture would mean food shortages worldwide. Manufacturing would halt in many regions. Transportation would be disrupted. Supply chains would break. For countries dependent on food imports, many countries in Africa, parts of Asia, the Middle East, a global supply chain disruption would mean famine. Now, let's return to North America and see what happened next in the simulation. By day 14 of the blackout, a critical decision was being made at the highest levels of government. The power grids in other parts of the country, those that had maintained power or had experienced less severe blackouts, faced a decision. Should they attempt to reconnect with the collapsed eastern grid, or should they focus on maintaining their own systems? This was a genuine dilemma. In a normal blackout, you want to reconnect all the pieces of the grid as quickly as possible. More generating capacity means you can restore power to more people. But in the simulation, reconnecting to the eastern grid risked spreading the blackout. The eastern grid was severely damaged. The transformers were failing. If you connected fresh, functional power to the damaged eastern grid too quickly, the cascading failures in the eastern grid could spread to the western grid. You'd essentially be connecting a functioning, healthy power system to a severely damaged system, and the damage could spread. Connecting the eastern grid back to the rest of the system, before it was fully restored, could cause cascading failures that would spread the blackout to areas that still had power. It was a terrible choice. Either you let people in the eastern US continue to suffer in the dark and without power, or you risk plunging more of the country into darkness. The decision was made to keep the grids separated until the eastern system could be substantially restored. Power would be restored region by region, but the damaged eastern grid would not be reconnected to the rest of the system until it was sufficiently healed to handle the connection. But this created new problems. The western grid, for example, normally receives significant power imports from the eastern grid. Now it had to meet its own demand from its own generation. Some areas saw power rationing. Some areas had to accept rolling blackouts or partial outages. It's a bit like a patient on life support where the main organs have failed, and the only way to keep them alive is to shut down the peripheral systems and reduce the demand on the system. You're essentially accepting damage to areas that were still functional in order to avoid spreading the catastrophe. By day 21 of the blackout, the situation had stabilized in some ways. The military had established supply lines. Food was being distributed, though in very limited quantities. The water situation had improved slightly in some areas as crews manually restored water pressure using portable generators. But the psychological toll was becoming very apparent. In cities across the eastern United States, people were beginning to accept that power wasn't coming back soon. The initial panic had given way to desperation. The social order was beginning to fray. Hospitals had established protocols for treating the most critical patients, knowing they couldn't treat everyone. This meant making horrifying choices about who got treatment and who didn't. Law enforcement was being overwhelmed. The National Guard was attempting to maintain order, but there weren't enough soldiers to police a continent-wide blackout. By day 30, 1 month into the blackout, the mortality rate was climbing significantly. Starvation was becoming more widespread. Disease was spreading faster than ever. The American healthcare system had been reduced to emergency triage in the few remaining functional hospitals. Hospital administrators had essentially surrendered to the reality that they couldn't help everyone. They were treating only the most critical cases and those most likely to survive. They were rationing medications. They were turning away patients because they simply didn't have the resources to treat them. The economic impact was profound. Businesses across the country were failing. Supply chains were broken. Manufacturing had halted. International trade had essentially stopped. The global economy was contracting at a rate that exceeded the Great Depression. Stock markets worldwide had been closed for weeks, not officially, but because there was no trading happening and financial systems weren't functioning. The value of currencies was becoming uncertain. If you couldn't verify that your bank still had your money, if you couldn't trust that the financial system would continue to exist, why would you hold currency? There was actually a reversion in some areas to barter. People were trading goods directly, food for tools, tools for medicine, medicine for services. The simulation estimated that it would take approximately 7 to 10 years for North America to return to its previous level of electrical infrastructure. During those 7 to 10 years, there would be a gradual process of recovery, but it would be uneven and painful. The scenario wasn't all doom and gloom, though. The simulation also modeled human resilience and innovation. There were stories of communities coming together. In some cases, small towns managed to restore local power generation using temporary generators. Agricultural areas adapted to manual farming practices. Communities that had local manufacturing capacity found ways to produce goods without electricity or with minimal electricity. The military, despite the logistical challenges, managed to establish distribution networks. International aid came from countries that were less severely affected. The global community, recognizing the existential threat to human civilization, mobilized resources in ways not seen since World War II. By year 2 of the recovery, North America had rebuilt roughly 30% of the power grid capacity that had been lost. It wasn't full recovery, but it was enough to restore power to some areas, particularly rural areas and smaller cities. By year 5, that number had climbed to 70 to 80%. The grid was partially functional across much of North America. Power was available, though possibly rationed. Industry was beginning to restart. Food production was improving. It wasn't until year 7 or 8 that the grid was largely restored to pre-storm capacity. But the simulation also showed that civilization had been irrevocably changed. The centralized infrastructure that modern society depends on had proven to be fragile. The social contract had been severely tested. Some areas had managed better than others, and the disparities created by uneven recovery created long-term social tensions. Communities that had prepared, that had local food production, local water sources, local manufacturing, they fared better. They recovered faster. Their citizens suffered less. Communities that had relied entirely on centralized infrastructure, that had no local resilience, they were devastated. Many people fled those communities, seeking areas with better access to resources. There was also a shift in how people thought about the future. The simulation showed that after experiencing the catastrophe, people were much more interested in preparedness. Communities began establishing local food storage. Municipalities invested in backup power systems. Governments created strategic reserves of critical equipment. It was expensive, and it required resources that the recovery process was straining. But people understood the stakes. They understood that they needed to reduce their dependence on centralized infrastructure. Now, let's talk about something crucial. How realistic is this simulation? The short answer is very realistic. The calculations of solar physics are based on established physics. The models of how coronal mass ejections travel through space are based on observations of actual CMEs and on established plasma physics. The modeling of the power grid is based on actual power system architecture. The engineers who worked on the simulation had access to grid data showing exactly how transformers are connected, how power flows, what the protective systems look like. The cascade failure modeling is based on known failure modes. This isn't speculation, it's physics. The epidemiological models for disease spread are based on historical data from previous outbreaks and on established models of how infectious diseases spread in populations. The economic models are based on actual economic systems and historical precedent. We've seen economic collapses before. We know how they unfold. Is there uncertainty in the simulation? Absolutely. The exact sequence of events might be different. The cascade of failures might unfold slightly differently. Some estimates might be off by a factor of 2 or 3. Weather conditions during the storm could affect how the geomagnetically induced currents flow through the ground and into the power system. The regional distribution of the storm could be different. But the overall picture, massive power grid failure, water system collapse, food system disruption, disease outbreak, economic crisis, millions of deaths, that's not speculation. That's physics and engineering coming together to predict what would actually happen. And here's the thing that should really concern you. We're not particularly well prepared for this. NASA and NOAA have excellent space weather monitoring. We can see solar storms coming. We have early warning systems. But beyond that, our preparation is spotty. Some power utilities have hardened their transformers against geomagnetic storms. Most haven't. The cost of hardening the entire power grid is estimated at about $2 billion. Let me put that in perspective. Americans spend about $3 billion on pizza in a single year. The government spends more than $2 billion on many projects that have far less direct impact on civilization survival. But it hasn't happened because there's not a clear agency responsible for doing it, not a clear funding mechanism, and no immediate political constituency demanding it. Solar storms aren't visible the way that hurricanes are. They don't knock on your door the way that floods do. They're abstract, invisible, statistical. Some governments have taken steps. Canada has actually installed protective equipment at some critical substations. The European Union has established guidelines for protecting transformers. But it's not systematic. It's not comprehensive. Most of the power grid infrastructure in most countries is still vulnerable. Now, let's talk about what would need to happen to truly be prepared for a major solar storm. First, you'd need to harden critical power infrastructure. The most cost-effective approach would be to install what are called series capacitors or other protective devices at critical substations. These devices would limit the geomagnetically induced currents that could damage transformers. Installing these at perhaps 200 to 400 critical substations across North America would dramatically reduce the risk of a continent-wide power grid failure. Second, you'd need strategic stockpiles of critical replacement equipment. Having a few dozen large power transformers stockpiled somewhere, ready to be deployed if needed, would ensure that critical infrastructure could be restored more quickly. Third, you'd need better communication protocols for the event of a grid-wide failure. If the electrical grid goes down and communication systems are impaired, how do you coordinate recovery? Fourth, you'd need strategic stockpiles of fuel, not just for emergency services, but enough to keep critical infrastructure running for weeks while alternative power generation is brought online. Fifth, you'd need to ensure that hospitals, water treatment plants, and other critical infrastructure have adequate backup power and fuel. Sixth, you'd need to work with international partners to ensure that global supply chains could be maintained even if one region lost power. The good news is that most of this preparation doesn't require inventing new technology. It's mostly a matter of engineering, logistics, and will. So let's talk about something else. What if the simulation had modeled an even worse scenario? The 1859 Carrington Event was powerful, but evidence from ice cores shows that the sun has produced much larger storms. There was a massive storm in the year 774 CE that was actually estimated to be around 10 to 20 times stronger than the Carrington Event. If Earth got hit with an event that strong, the simulation becomes even more apocalyptic. Not just the power grid, but satellites, electronics, infrastructure worldwide would be damaged far beyond recovery on any reasonable timeline. We're talking about potential civilization-wide collapse. The probability of such an event in any given year is low, but it's not zero. Scientists estimate the probability of a Carrington-level event in any given year at roughly 10 to 15%. The probability of an even larger event is much lower, maybe 1 to 5% per century. But again, it's not zero. In other words, there's approximately a 1 in 10 to 1 in 15 chance that in the next year, the sun could produce a coronal mass ejection that would hit Earth and cause the catastrophe we've been describing. That's the kind of probability we take seriously for other risks. We spend billions of dollars on earthquake preparedness even though the probability of a major earthquake in any given year is much lower than 1 in 10. We spend billions on pandemic preparedness even though the probability of a pandemic has historically been lower than the probability of a major solar storm. Now, as we conclude this exploration of the 2026 simulation, let me address one final crucial aspect: the question of what comes after. The simulation didn't just show us the disaster, it showed us pathways through it. And that's the thing that should give us hope. We're not doomed. We have choices. We have agency. What we need is political will. We need governments and institutions to recognize that solar storm preparedness is not a luxury. It's a necessity. We need funding to be allocated. We need infrastructure to be hardened. We need contingency plans to be established. We need communities to build resilience. We need local food production, local water sources, local manufacturing capacity. We need to accept that modern civilization, for all its wonders, is fragile. We need to reduce that fragility. The sun will continue to shine. It will continue to power life on Earth. And occasionally it will send a storm our way. The question is, will we be ready? This is what the simulation teaches us. This is what the physics tells us. This is what we face. The sun is beautiful. It's the source of all life on Earth. It's the engine that drives our planet's weather, our climate, our existence. But the sun is also powerful, more powerful than human civilization. And occasionally it reminds us of that fact. The question is, will we listen?